welcome back. In this particular video, we will be discussing the problem. Count the number of 1 bits in an integer. 1 bits, or you can say set bits in an integer. So count set bits is the problem. The problem is we have to write a function. What it will do is it will take an unsigned integer as input. It means it will take a positive integer as input of 32 bits, because in the question it is given 32-bit unsigned integer will be given. So 32 bits number, which is always positive, is given as an input. What we need to do in that number is we need to find or return the number of 1 bits, set bits, 1 bits, or you can say the bits which are equal to 1, which should be the output. And the number of 1 bits is also known as Hamming weight. Basically, count set bits is nothing but counting the or calculating the Hamming weight of a given number. So let's basically take a number which I am saying, although it will have 32 bits, but for simplicity, let's just have a number 101001110. So I am only taking how many bits? I am just taking 1, 2, 3, 4, 5, 6, 7, 8 bits. If we are able to deduce a logic in 8-bit number, we will also be able to deduce a logic in 32-bit number. It is just extending it to 32 bits. So always, whenever we work on bits, what is the bit index starting from? Always the bit index starts from the rightmost bit, that is 0, 1, 2, third bit, fourth bit, fifth index bit, sixth index bit, and seventh index bit, because there are total 8 bits in this number. Obviously, we can assume the rest are all zeros. How many set bits are there? How many bits are 1 in this? As you can see very clearly, there are 4 set bits. So output should be 4, answer should be 4. Even if you take other test cases, if input number is 5 binary representation is 1, then you can say 0, 1. That is 4 plus 1, 5, and then remaining all zeros. So how many set bits are there? Only 2 set bits are there. Output is 2. So given the number in an integral form, given the number in a 32-bit integer, you don't have to actually find out the binary representation. You have to work on bits. So for that, prerequisite will be bit manipulation. You should know how to use left shift operator, right shift operator, and operator, or operator. These kind of bit manipulation operators you should know. Then only you will be able to solve it. Otherwise, it will be very difficult to first generate the binary representation and then count the number of ones. So given a number, how we can count the set bits? That is actually the question. But approach 1, very simple. If you know how to check whether a bit is set or not, what you can do is you can run a loop over all the bits and check whether they are set or not. Check set bit for each bit in the range, for each bit in what? In the range 0 to 32 minus 1, 0 to 31. And whenever you get the check set bit as true, you will say count plus plus. That is, somehow you will implement a function which will check whether the 0th bit is set or not. You will say false. So don't do count plus plus. Initially count will, you can say, will be 0. Then next, is the first index bit set? Yes, count plus plus or answer plus plus. Second bit set? Yes, count plus plus. Third bit set? No. Fourth bit set? No. Fifth bit set? Yes, count plus plus. Sixth bit set? No. Finally, seventh bit set? Yes. So answer will be 4. Now the point is, since we are going to run a loop on every bit, irrespective of whether the bit is set or not, it will take time complexity as equal to the total number of bits. So given a number n, total number of bits of a number n will be log base 2n. However, since the number is only containing 32 bits, you can say it is equivalent to order of 32 right now, which is equivalent to constant. So either you say logarithmic or you say constant, both are correct time complexity depending on the constraints of this question. What about the space complexity? This solution, which will check whether a bit is a set or not, will be just constant space. No need to use extra space. You will just create a mask to check whether a bit is set. We will also discuss how to create that, but space will be constant, no extra space as such. Now the point is how to check whether a bit is a set or not. So given this number itself, let's copy this number 2 times. One time I will take a bit which is set, and one time I will take an example which is not set. First, let's do a dry run for the third index bit. Actually, first let's do a dry run for the bit which is second index. 0, this is 0th index, first index, second index. So I am doing a dry run for second index to check whether the second index bit is set or not. To check whether a bit is set or not, what you need to do first of all is create a mask. And how should the mask look like? The mask should look like all the bits except the second index, which we need to check. should be 0 and the second index bit should be 1 in that mask. That is all zeros before the second index, all zeros after the second index. So this is the mask which we have to perform, which we have to create. And how we have to create this mask, how we can do it is, we can basically make a number which is 0, 0, 0, 0, 0, 0, 0, 1 and shift this 1 towards the left by how many places? By 2 places, by bit number of places. So this mask will be nothing but 1 left shift by bit number of times, whatever bit we are getting. If it is 2, 1 left shift 2 times. That is, make it go to the second index. Once the bit is left shifted by, once the one bit is left shifted by bit number of places and we are able to form the mask, what to do with this mask? We have to do the mask and with the number itself. That is, if I will do n and mask, what I will get is 1 and 0, 0, 0 and 0, 0, 1 and 0, 0, 0 and 0, 0, 0. Here also 1 and 0 will be 0, 0 and 0 will be 0. What about this? The operation and does what? Any bit and 1 will always give you that same bit. If it will be 0, it will give you 0. If it will be 1, it will give you 1. But when it comes to bit and 0, it will always give you 0. That's why all these bits are coming out to be 0. Because anything with 0, if you do and, it will always come out to be 0. But when it comes to bit with and with 1 bit, then whatever is here, it will come in the answer also, in the n and mask also. So since n and mask is nothing but a number which is not equal to 0, it is having a bit set. If a number is 0, all the bits will be unset, all the bits will be 0. Since this number is not equal to 0, we will say there is the second bit set. So we will return true, it is set. We have to check whether a bit is set or not. However, if I take the same number, but I want to check, let's say for third index, whether the third index bit is a set or not, it should give me false. How will it give me false? First of all, create the mask as done in the previous code. However, this time mask will be 1 left shift B, 1 left shift 3. That is, make the third index bit set, all other bits unset in the mask. And now do the mask and n. That is, you will have this value, this blue value as n. You will do n and mask. You will get the answer. All other bits will be 0, of course, apart from the bit which we are concerned of. But when it comes to the third bit also, 0 and 1 will also be giving you 0. So all the bits are 0. So this number entirely, number and mask, is giving you 0. So if it is giving you 0, you should return false. So this is how you will check whether a bit is set or not. And this is how you have to check for each bit one by one. Check for this first index, second index, third index, and so on. And whichever bits are giving you true, check set bits function, you will do count plus plus. This is a very good approach. No problem in this approach. The most optimized time, the most optimized space. You can't do better than it in the worst case. But the point is, you will have to write a little bit more code in this approach. There is an alternative approach, which is an algorithm designed by some scientist or mathematician. The algorithm's name is Kernigham's algorithm. I might pronounce the name incorrectly, but let's actually go to the approach number 2, which will be shorter in the length, in the, you can say, the total syntax for the code will be shorter in all the programming languages. Obviously, if you are not able to remember that approach, if you are not able to learn that Kernigham's algorithm, what you can do is you can go ahead with this approach. No one will stop you and no one will say that you are writing a less optimized code. Obviously, it is not less optimized, it is the best. You can't do better than constant. Obviously, less than constant is nothing. So let's check the same number. And what we need to do is, in the Kernigham's algorithm, the approach number 2, alternative approach, which will be a shorter code, is we will somehow directly jumps from set bit to the next set bit, from set bit to the next set bit. That is, if a number, let's say, contains 4 set bits, what this Kernigham's algorithm will do is run the loop for only 4 times, not 32 times. If a 32-bit integer only contains 4 set bits, run the loop only on those 4 set bits somehow. If the number contains 32 set bits, then of course the loop will run for 32 times. That's why the worst case will remain same. But maybe if the number does not contain any set bits, in that case, the loop will not run at all. So it is dependent on the number of set bits. The algorithm name is, I'm writing it also, Kernigham's algorithm. Kernigham's algorithm. It will run the loop on directly set bits. How will it run? It will start from the rightmost set bit. This is RSB I'm writing, rightmost set bit, and it will go to the leftmost set bit one by one. How will it do it? How will it basically go ahead is, it will try to convert, the Cunningham's algorithm will try to convert this number by removing the rightmost set bit. Let me write again. This is the rightmost set bit. This is the leftmost set bit. Again and again, what this algorithm will do is, it will remove the rightmost set bit and make it unset. That is, the new number after unsetting the first rightmost set bit will be 10, 100, 100. This is step number 1, or you can say count plus plus. Count is 1 now. First step performed. First rightmost set bit removed. Are there more step you can say set bits? Yes, there are 3 set bits. How to know whether there are set bits or not? If the number is 0, there are 0 set bits. If the number is non-zero, there are at least 1 set bit. Since this number was not equal to 0, there is at least 1 set bit. Since this number is also not equal to 0, there is at least 1 set bit. So somehow the algorithm will remove that set bit, and the new number after removing the rightmost set bit will be what? 1 0 1 0 0 0 0 0. In just one single operation, we will be able to remove the rightmost set bit. That we will discuss using the formula. But this number, although the count becomes 2, the second operation we are able to perform, still this number is not equal to 0. Still we are having some set bits left. So still count will continue. That is, we will still go to the next rightmost set bit and remove it. So what is the rightmost set bit now? It is this particular bit. I will remove it. New number will become 1 0 0 0 0 0 0 0. So count will become 3 because this is the third operation which we are able to perform. Although this number is also not equal to 0. So we will once more remove the rightmost set bit in this number, which is this particular bit. And as soon as I remove it, what will happen? The number will become all zeros bits. And the count will become 4. And since number have all 0 set bits, all 0 bits, not sets, unset you can say. So this number is equal to 0. So stop now. That is, we have counted all the set bits, which is 4. But the point is, how to remove the rightmost set bit from a given number. Let's say the number is n. How to remove the rightmost set bit from a number? You can use a very simple formula, that is n and with n minus 1. Just do the and of n and the previous number. And what it will do is, it will remove the rightmost set bit from that. That is, convert 10100 to 10100 Remove the last one and make it 0, make it unset. Similarly here, if this number is n, next number will be n and n minus 1. Now let's see how. Let's copy this number actually. Let's just again copy this number. Maybe let's copy it from the previous slide. And let's see that how the n and n minus 1 is going to remove the rightmost set bit. This will clear the rightmost set bit, clear RSB. So let me write the n minus 1 value. This is n value. What is n minus 1? You will say it will be 1 0 1 0 0 1 0 1. This will be the previous number, because this is nothing but 2. 2 minus 1 will give you 1, and this is 1. And other digits or other bits will remain same. And if you will do the AND between these two numbers, what will the new number become? These bits which are same will remain same. No change to them. But this 1 and with 0 will give you 0. This 0 and with 1 will give you 0. And this is what we are having after removing the rightmost set bit. As you can compare, this bit, which was the RSB in n, is removed in the output in n and n minus 1. It is not there. You can apply the same step one more time. Maybe if I can show you for one more time. It is not that much intuitive that why it is going to work, but this is a step which you can maybe cram. It is just anyways 2 numbers getting AND with each other. Although there is an explanation which you can try to find out, that is, whenever you do a AND with n minus 1, what will happen is, all the digits after the rightmost set bit towards the left will remain as it is. And whatever digits are before the rightmost set bits in n minus 1, they will be nothing but, you can say, they will be nothing but ones. And if you will do AND between them, since they will be opposite of these numbers, not ones, you can say opposite of the first number, n and n minus 1 will have opposite bits in these two places in here. So if you will do the AND between them, always different bits will give you AND 0. 0 and 1 will give you 0. 1 and 0 will give you 0. And these bits will remain same. And what will happen to the RSB? If n is having RSB as 1, n minus 1 will have RSB as 0. This is very important because you are subtracting the number. And if RSB, we are subtracting, the 1 from RSB will become 0 always. Like it will never happen that the highest bit is becoming 0. Lowest set bit will become 0 first. That is how you will subtract. So let me just give one more demonstration. From this number, if I will do the n and n minus 1, 1, 0, let me write in different color. 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0. So this is something, then 4. In decimal, it will be 4. So what will 4 minus 1 will give you? 4 minus 1 will give you 3. What is 3? 0, 1, 1. This is 3. And remaining will remain same. That is what? The lowest bit, the rightmost set bit will become 0 when you will do n minus 1. So this is n, this is n minus 1. And if you will do and between them, the new number will be 0 and 1. Different bits become 0, different bits become 0, different bits become 0. And all these remaining bits will remain same because they are same in both n and n minus 1. So you are again able to remove the rightmost set bit. This bit is gone now. It is unset now. So the optimized algorithm will be not optimized, but alternative approach will be do update n, make n become n and n minus 1 again and again, again and again, again and again, and do the count plus plus till the n reaches 0, till it not become 0, run the loop. As soon as it becomes 0, stop. So we will actually write the instruction manual using this Cunningham's algorithm directly. So what we gotta do is, we can say, let's maintain a count, set count integer as 0 because we have to return integer. At max there can be 32 set bits only. Run the loop, preferably a while loop, till the point this n variable does not reach 0. If it is not equal to 0, till that run the loop, because if all bits are 0, then there is no more bits to be counted which are set. But how to remove, how to clear the rightmost set bit? It is, the procedure is update n as the value n and n minus 1. Update the n, the same variable, by this value, and also do the count plus plus, increment count by 1. That is the number of times this loop will run. The number of iterations in Cunningham's algorithm will be equivalent to the number of the set bits or the Hamming weight. And now you can return the Hamming weight, you can return the count. So this approach, as I already discussed, in worst case, it will remain same. It will remain logarithmic only, because in worst case, all bits can be set in the number. If a number is 32 bits and all 32 bits are set, it will go to each and every bit and remove it one by one. So worst case will still be logarithmic. However, in average case, you can say it will reduce the time complexity a little bit because we are just going to set bits, not all the bits. But worst case will remain same. And if n is given to you as 2 raised per 32, or you can say if the number of bits log n is given to you as 32 only, so it is order of 32, which is still constant. So both approaches, previous approach was also constant time, constant space, although it was going to all the bits, this particular approach, and the current approach also is going to all the bits in worst case. So same time, same space, constant time, constant space. However, smaller code, a lot of you can say length of the code or function altogether. The check set bit you have removed now. So given this instruction manual, we will be using it in milestone 4 to write the code in Java language. So first we have to count the number of set bits. So we will create a count variable set to 0. We will do count plus plus till the time the loop runs and the number does not become 0. As soon as the number becomes 0, we have to stop. This loop will only go to set bits. How? We will one by one clear the set bit, clear the rightmost set bit specifically by updating n as the n and with n minus 1. Do the and of n with the previous number, with one smaller number. And whatever number of times this loop will run, that is the number of set bits. So count plus plus each time in the loop and return the count. As simple as that. So if I would have removed all these comments, all these steps which I have written in the instruction manual, this will be just 4 lines of code, nothing much. So if I will run this, hopefully it should get accepted for sample test case. For the number 5, which is represented in binary as 101, it should give me 2 set bits. Only 2 bits are there which are set. So let's see. As you can see, for 3 also there are 2 bits, although the input was 5. But when it is running, it is checking for 3. Let's take a very big number. Maybe let's take a number which is 158. Any random number I have taken. I'm not sure how many set bits will be there. Although in the constraints they have mentioned the maximum number can be 2 raised power 32 minus 1. That's why they have taken a long data type. So in this number, there are 5 set bits. It is working correctly. Let's submit now and actually see whether the logic is working for every kind of test case or not. It is taking some time. And as you can see, all the 23 test cases are passing. The time complexity of this code will be logarithmic, log base 2n, where n is the unsigned integer. However, since the number of bits, log n is nothing but the number of bits, given in the question is only 32, either you can say log base 2n is the time, or you can also say order of 32 is the time. And since order of 32 is order of 1, so it is also constant time, because log n is very, very less when n is very, very less. So log n or constant time complexity, and the space, since you can see there is no extra data structure, no extra auxiliary thing which you have created, no recursion, nothing like that. So constant space. So constant time, constant space solution for this problem. With that, we are done with this.